Here. I'd like to thank everyone for joining us today. Today's topic is what are the credentials of the BMPs you're specifying? Taking an in-depth look at some of the credentials you should be finding on their product resumes. Before we get started, I'll briefly go through some of our presenter here and myself. My name is Jeff Benty. I'm your moderator for today's session. John Mall is our speaker. John received his education at the University of Florida. He's a geologist. John, over the years, has gained invaluable environmental experience while working in the mining and landfill industry. John is in conjunction with Clark Hughes, are the inventors and owners of the crystalstream technology, a stormwater treatment product currently available on the market. And John currently operates as the CEO and oversees and directs all research and development and engineering services for crystalstream. At this time, if you'll please join me in welcoming John. John, the floor is yours.
Thank you, Jeff. Hoping the audio is good here, folks. I need you guys to let me know if you have a problem, or let Jeff know. One of the little things about this particular interface is that when I'm a panelist, I can't see regular chat. So, Jeff, if you'll help me out with that if there's a problem. And by the way, Jeff, I think that's a week of unpaid vacation for assigning me to the University of Florida instead of Florida State. But we'll talk about that privately later. Folks, I appreciate you being here today. And we want to talk a little bit about how the credentials of a product actually have changed over time and how people have had to try to evaluate black boxes. I have some jurisdictions whose solution to using the black box manufactured BMPs is to essentially not use them at all. And so they write impossible testing protocols and other things that no one could ever qualify for. Then we have others who've worked really hard to provide a level playing field. I think we've got a gentleman in the audience today, Richard King at Marietta, Georgia, that threw out a specification, I guess 7 years ago now, maybe more, maybe less, that said, hey, here's my specification. All you have to do is meet it. And I think competition is fair and level in the city of Marietta. And I know it can be done because others have done it all over the country. But we've learned some things over time, and I want to present those today to talk to you about how to properly specify BMP and to make sure that you've got good credentials. Well, obviously the task is to find a BMP that meets the requirements of your jurisdiction. And I'm not just talking to regulators here. When I say your jurisdiction, for an engineer, it's the jurisdiction that you have to get a permit approved in. Now, at one time, the literature of manufactured BMPs was accepted as more or less the gospel. And it's kind of ironic that that's really still true today for public domain BMPs. Now, we've learned as manufacturers that, man, you better pay attention to what's coming off the site, that a road's different than a kindergarten, or a big box retail is much different than a dentist office or a gas convenience operation. And so, but on public domain BMPs, the literature is the manual. The literature says it's 80%, so it's 80%. And, you know, there's some great places to put sand filters and some great places to put ponds and some great places to infiltrate. But actually, every one of these things are manufactured. There's very, very few natural BMPs that are out there. Now, I've seen some natural BMPs where riparian buffers were used essentially as a filter strip, where nothing was allowed within 100 feet of the river for discharge, and the water had to travel over land. But most all BMPs are man-made. Over time, the claims of magic removal rates became more and more prevalent for manufactured devices, and this can be understood by the fact that there's intense competition, excuse me, obviously, in all sorts of construction products. This would include asphalt and concrete and other, excuse me, other similar materials. And over time, the National Precast Concrete Association and others arose to take this confusion out of the marketplace. Organizations like ASTM and others arose to give common standards. This is something that's been missing in the water quality. And the other part that makes it very tough is that the definition of water quality is very, very loose. The EPA said, well, you can't test for everything, and we certainly aren't going to go out and catch water samples in a bunch of storms on a bunch of different properties and analyze them in the lab. So we figure if you get 80% of suspended solids, you're pretty good. You're getting everything that we think you should get. It's a nice surrogate, and that's fine. And then they said, well, the water quality storm, it has to be defined by it being a certain percentage of the rainfall, and a lot of that's left to local areas because, let's face it, rainfall is much different in San Diego on the West Coast than it is in Seattle. It's certainly much different in New Jersey than it is in Key West. And you have to understand what that 90th percentile or 85th percentile storm is. And part of what was assumed, and I harp on this too much, so I'm going to let it pass today, that a lot of people think the worst stuff washes off in small rainfalls event, and the bulk of stuff washes off in small rainfalls events. And I'm sure that the science indicates otherwise. So there's a lot of different assumptions out there for how to do water quality. And so to the table come manufactured devices, proprietary and public domain. And the idea is we have to find some way to know if they're working. So we have testing. All testing is certainly not created equal, and I want to bring out some points here. A lot of people claim they have third-party testing. And third-party testing, if you go look it up, it's paid for and conducted by others without any control or vested interest from the manufacturer. You walk into Home Depot and you get a brick that's one of thousands and thousands, and you test it through the ASTM standards to see if it has the strength and if it has all of the characteristics that it's supposed to meet. That's a third-party test. And then the third party publishes that test. For example, in our industry, the ETV testing was done essentially third party, where there was a small fee charged to a manufacturer, but it was probably 1/50th of the cost of the test. And that was for the preparation of the report, because the EPA hired a consultant to take the field data and write a report to their standards. Second party testing is usually conducted to a specific standard or protocol. This would be like NJDEP or Washington tape, or in Georgia, for example, where I'm sitting today, there's a new standard that's been proposed, GTAP, and that testing is supervised and conducted by others, but paid for by the manufacturer. So there's a certification process with an independent observer or a certified lab, things like that. Now, if you do a second-party test and you don't get a good result, that test is unlikely to see the light of day. This is in contrast to, for example, the ETV testing. In Georgia, on the Griffin site, one device they never could make run actually function. If you go look through, I'm not going to pick on them. They've never sold it commercially, I don't think, since then. And so, but it just couldn't. It never functioned. They couldn't test it. They couldn't get the water out the backside of it. Other devices claimed 80 and got 40, and claimed 80 and got 60, and so that didn't make people happy that they were tested by a third party and that they had no control over how those results came out. Self-testing is usually conducted by a manufacturer under conditions and using a protocol favorable to the product being tested. There's one famous baffle box out there that was tested by a professor at a fairly obscure university using 2,000 micron sand. My goodness. If you can't catch aquarium gravel in a water quality storm, you probably need to be doing something else. But the point I'm making is all this testing that you see out there is not necessarily the same, and there's been an effort underway to come up with a kind of a level playing field. Now, third-party testing, again, is invaluable, but it's not fair to say, well, that's what you got to have. Because if you come up with a new product, how are you going to convince someone to take your product, pay for a test, and give you the benefit of $250,000 to $500,000 worth of lab work and field work? You can't go buy one. You can't request one. You can apply to at least to a grant project and hopefully get accepted. And that was the modus operandi in the ETV testing. There was a grant, a TEA grant, and everybody applied, and those that met the application got accepted. So But when it's there, it's definitely the best thing to have, obviously. Now, second party testing to a protocol is good, but when the protocols vary widely, you can't take a test that was done in, say, Washington State, or one that was done in New Jersey, or one that was done in Georgia or Virginia, and really make an apples-to-apples comparison unless the protocols are the same. And some protocols say you have to have field testing only. This would be, for example, Knoxville, Tennessee. They want to see your lab testing. They've got a certain set of standards. Everybody applies to the same standards, and the chips fall where they may. Laboratory testing, Knoxville's laboratory testing, field testing only. There are a lot of places that take field testing only, and some, like New Jersey, do both. Knoxville's a laboratory. Most of Georgia has been field testing. Some places want to see both. Now, most land-based BMPs obviously can't be tested in the laboratory, so you're not really sure if you got 80% or not. I would point those of you who are interested to the City of Charlotte BMP studies. They were done by NC State University, and they tested every one of the North Carolina 85% removal BMPs in that study, and they found that none of them removed 85%, of course. Then they lined up a bunch of proprietary BMPs on their bus terminal, declared that everybody failed. It was a very, very tough environment. There were irreducible flows came in. In fact, I was embarrassed for the people that did the study because some of my competitors were shown to have no removal of anything. In fact, they manufacture pollutants constantly all day long and spit them out to the environment. So, but there's some important things to look at in those studies. And one of them was that the effluent quality, what was getting to the stream, for example, in my device tested there, was lower and better than the effluent quality of the water coming through their manual approved BMPs. Every field study is extremely useful, no matter what the results. You could say, hey, I passed or I failed, but you learn from those field studies. Those land-based BMP studies that were done in Charlotte are among the very few where there's good QA/QC testing done on field-based. And some things like a sand filter are just so difficult to match influent to effluent. You really have to look at composites and some other things. Well, test protocols are not equal either. On field testing, they have to have an acceptable storm. Usually they want 15. Sometimes they want 0.15 inches within 25 hours, sometimes 2/10 of an inch within 24 hours. Some people want to limit heavy storms because they feel it gives an advantage to proprietary devices, for example. And they only want small storms because they believe only the small storms are important. And then after you decide your acceptable storms, you have the sampling methods. Is it graph sample? Is it automated samplers? Then you have to match the upstream to downstream pairs. You have to have pairs. Or you collect 14 samples in the storm upstream and 14 downstream, and you composite them, and you get a general overall sampling basis. You have to get flow weighted in some cases because a sample that had higher flow and higher concentrations might be, quote, worth more. So there's a lot of things that come up into a test protocol. Going back again to the ETV, what's one of the reasons I like it is because it has been consistent, and everybody, fortunately or unfortunately, got subjected to the exact same analysis method and the same samples. And then finally, you do have to decide, how are you going to analyze these samples? TSS, SSC, turbidity. If you're looking for solids, there's standards for testing phosphorus, whether you want to look at total P or dissolved phosphorus or particulate. So there's a lot to how these test protocols are written. For lab testing, you have to set a flow rate. And in general, you want to build a curve. Most people will take a target flow rate and test at 25%, 50%, 75, 100. That's kind of what NJDEP has asked people to do at New Jersey DEP. And then NJDEP is interested at 125% of that flow rate. When we tested in the lab, we went up to, I think, 9 times our flow rate. We really wanted to blow everything out of that device if we could, but all of that in a lab test protocol, you have to decide what you want to test. The size and concentration of the particles, particle size definitions, everything. If you tested my device with 20 micron particles, at a high flow, I would probably score a 2 or 3% removal rate. Tested with the 2,000 micron particles that the one fellow did for self-testing, I would be a hero. I'm 100% removal at all flows, and we could declare water quality finish, and everybody could go home. So size and concentration of particles is important. And we used to think concentration in milligrams per liter was very important. We would test at 100 milligrams per liter, 200 milligrams per liter, 300 milligrams per liter. There is some variation when you get down to 100 milligrams or 50 milligrams per liter. But in reality, the concentration has a very small impact on the testing. And so to save money, save time, we found that one concentration of about 200 milligrams per liter is probably pretty good. And then the method of injection. Are you pouring in dry sand? How do you make sure it's coming in at 200 milligrams per liter? Is it a wet slurry? Is it injected in the top of the pipe, the bottom of the pipe, the middle of the pipe? I mean, there's lots of things that can vary. And then the sample points. Where do you sample? Do you sample one pipe diameter from the entrance to the device to get influent, or how many pipe diameters below the injection point? A lot of things. So how you collect it, and then how do you analyze it? So all these parameters vary greatly over time, and a real comparison of testing has been very difficult. Dateline 2000, July of 2008 in Holden, Massachusetts. I had a hand. In fact, I declared myself Emperor of Water Quality and started the MWQPA, the Manufactured Water Quality Products Association. Made myself Imperial Potentate, set standards, did some, had a mission statement and a code of ethics and all these things. And when I did that, I invited all my competitors to come to a central point, fire me, and form an association to replace what I started. But believe it or not, 8 or 9 guys joined what I started, because I said, you know, the real enemy is we don't have standards. We don't have protocols. People are accepting a wet pond for 80% all over the country, in places where it makes total sense and in places where it makes no sense. Over and over again, we saw the real enemy was not each other, although we compete fiercely every day. The real enemy was the fact that it was the Wild West. There was no standards. There was no rules, and even less rules in the world of public domain. And so we decided we wanted to promote. We named the organization SWEMA. MWQPA was thrown out as being a really dumb name, and I've never held any grudges about that. But SWEMA, the Stormwater Equipment Manufacturers Association, was born on the steps of Alden Laboratories, a neutral site in Holden, Massachusetts. And we said, let's look for standards, performance-based testing, and real-world results. Our real focus has been to keep our eyes on the watersheds first and foremost. That sounds like a lofty goal, but that keeps turning us back to the science and the real performance of our devices. So the first time we had a united voice as stakeholders in these developments of protocols. And even though the products are very diverse and our positions on how to test were very diverse, everyone was interested in fair treatment, equal opportunity, and good water quality. And we managed to adopt the ASTM methods. Those of you who are familiar with ASTM understand how that works. All the stakeholders come to the table, everybody gets a say, and you come up with a consensus, a balanced consensus of a standard. In August of 2009 in New Jersey, SWEMA wrote a letter to NJDEP and said, you know, you've let people test with large particles, some people with small particles. The laboratory protocol has been all over the place. And then everybody, regardless of their test results, is listed at 50% removal. And, of course, at New Jersey, you're asked, that's a two-pronged lab testing and field testing. Then to go to the field to verify your lab results. Some people went, some people didn't. It was a real hodgepodge. And we said that it wasn't a level playing field because everyone was level at 50%. But why not test with bigger particles? Why not test a different way? So we were astounded. I say to the great surprise, we were astounded at SWEMA when New Jersey said, okay, if you guys are so smart, you write the protocol. Let's get a level playing field. But you're going to have to agree. And it's going to have to be your members and non-members as stakeholders. So we set about and did that. An update here is that lab testing standards are emerging. concurrent with what SWEMA and New Jersey DEP were doing, the respected ASTM organization in their Concrete 2770 committee has progressed with a standard laboratory protocol and testing protocol, very similar to what SWEMA has done. In fact, people on that ASTM committee were also on the SWEMA technical committee, and the results are essentially the same, some slight differences there. But these efforts solve one of the basic problems, and that is, how can we compare apples to apples with testing? It would be good. A lot of people applauded our efforts and the ASTM efforts, and these are getting ready to be published. But there's some serious issues out there, and this is the piece that I wanted to concentrate on, and this is the piece that remains of what we really need to think about as manufacturers, specifiers, and people that are in charge of the water quality in watersheds and in jurisdictions. There's two major problems out there. The first one is the laboratory testing conditions bear absolutely no resemblance to actual field conditions and cannot predict field performance. The best you can say about laboratory testing is a very good comparative analysis where you can look at what one product was able to achieve and what the next product was able to achieve at the same speed and roughly the same size. Lacking anything else, I'm not being critical at all of those jurisdictions who only look at laboratory testing, because otherwise you've got no standard. And so you should keep it in the back of your mind that laboratory testing with pure silicon sand material at a certain size may or may not have much to do with how a device would actually work in the field. And it's important to recognize that. And that's a problem we haven't solved yet. Now, once we have good apples-to-apples laboratory testing, we can start to look at field results and see how those laboratory tests relate to performance in the field. And that's going to be a happy day when we will start to build some models where we can do excellent predictability. And we're going to improve the laboratory testing too. Laboratory and field testing are very expensive. Typical lab test is $50,000 to $60,000 if it's done correctly. And they're limited to one model of a device and one test regimen. One model of a device more or less in the field, because field testing can go between $250,000 and $500,000. So once you get a lab test and a field test, how do you project those results to other models of the device? I've showed the guy adding 2 and 2 and coming up with 22. And unfortunately, even when testing has been done, there are people that believe there's some voodoo magic in how you can scale between model sizes and come up with a new untested model, but use your testing on a smaller device or a bigger device. The first problem I mentioned is obvious to anyone, that the lab and field conditions are just not the same, because a constant flow with a constant concentration in the lab and a constant particle size distribution just doesn't happen out in nature. Flows aren't constant, concentrations aren't constant. Even at the same flow, the beginning portion of a storm, the building up limb, the rising limb of a storm, if you will be carrying more material typically than the falling limb of that same storm at that same speed. Particle size distribution, smaller particles tend to wash off first. As velocities pick up in gutters and in pipes, the larger particles begin to move. And so the particle size constant distribution is also a constantly changing target. And storms don't happen as they start low, build up big, peak, and go down. They are all over the map as far as intensities, times, and delivery. So all these factors mix together, and it's very difficult to say, wow, I got 80% of the lab of this, so I'm going to do really well in the field. The density of materials varies from less than water. These are materials that float like duck feathers on the pond out there, to things that are many times heavier than silicon test sand. We have liquids, we have dissolved materials, we've got organics. And the materials coming to a BMP, they change based on the antecedent conditions. Did it rain hard yesterday, and now I've got another flow and of the same amount, but there's nothing to wash off. Solids mix. Things stick to each other. Clay sticks to sand. chemistry happens. The pH changes. Heat is added. Materials meet that where clay wants to absorb metal ions. And then there's long idle periods in a BMP, whether it's a pond or a vault, where anaerobic conditions can occur. So there's a very complex physicality and chemistry out in the field. So why do we test in the laboratory? Well, as I mentioned earlier, it gives us a basis for comparison of technologies. It is, however, interesting to note that overall, if you go examine the NJDEP data and the ETV data, those devices which tend to catch 80% of, let's say, an average 90 micron mix of particles, all tend to hover around 20 to 25 gallons a minute per square foot. So laboratory testing also tends to kind of support that. It shows the hydraulic limitations of a technology. The one I talked about in Griffin would never have been put in the ground if somebody had figured out that the weirs in it would not work as conceived. There was a major manufacturer that had to lower the bypass speed on all of his devices, the published speed, because he'd never taken it to a lab. Now, he had calculated a circular orifice pushing so much water to a manhole on the side, but it turned out circular orifices that size don't work very well when you look at Manning's equation. And there were some other things, some flow restrictions that hurt him. So long story made short, when you get in the laboratory, you know what the hydraulic limitations of a technology are. For example, we measured the head in the front and the back of my device to solve a long-running head loss argument. When we got in the lab, we knew exactly what our head loss was. And then you're able to develop a performance curve for the device. And that performance curve can be looked at as a way to, as particle sizes change, you can do some good math and talk about how your device's performance would degrade with smaller particles and how it would improve with larger particles. And you can get an idea, along with examining the contents of your device, how well you're hitting the sweet spot in your designs. It actually, in our experience here at CrystalStream, we lowered the flow, the published flows, on 2 devices and raised them on 2 devices based on what our laboratory testing showed and what our experience in the field. Interesting stuff. We never could have known that without being in the lab. If you test more than one size of a device, of your own device with similar geometry, you can verify scaling methodology instead of just accepting service loading or volumetric scaling. You can get a real scaling methodology. And by the way, that also changes by speed and some other things. So untested models can be projected. At least you've got 2 points, data points on the line. Really, you'd want to test 3 to start formulating a curve. And the field conditions are known. And you've got good lab testing. You know the particle size distribution. You know the flows. You know the site geometry. Now, realistically, you guys know it's very seldom. In fact, I've never seen a set of plans come into my office and go, oh, by the way, here's the particle size definition for what's going to run off of the site. First of all, the site isn't built. And secondly, if it is built and we're doing a retrofit, it's very unlikely someone has collected 15 storms or so to see what the particle size definition is. But if you got a good idea from similar sites, and you know the flow, and you know the site geometry, the slope of the gutters, the pipes, you may be able to use laboratory testing to produce, to really get pretty close to a good suitability of a device on a site. So laboratory testing is certainly valuable. Second problem is a little tougher. Second problem is, how can you test a single device, one size device, and then use that test on all these different devices? And I'm using the example here of a really small car being tested, and then you project that up to, I think that's the only Porsche limo I've ever seen, but project it up to something much, much, much bigger. And when I say much bigger, sometimes these things are bigger by a factor of 30 or 40. The financial realities limit testing, especially field testing. It's very difficult. For example, in Georgia, I'll give you some numbers. Most of the companies in this field will dedicate 3 to 4% or sometimes more, depending on the year, to research and development and testing. That's of our top line. In Georgia, they want us to have 4 field tests for GTAP for each soil type. Now, on my soapbox for a second, a Burger King in the mountains, I'll guarantee you, in Helen, Georgia, is pretty darn close to Burger King. In Savannah, as far as what's on the site, asphalt's about the same, soil's about the same, maybe some little bit different slopes. So there's not a ton of difference. But Georgia wanted 4 tests and in the 4 soil types. And at, let's say, $250,000 a piece, $1 million worth of testing. You project that up, we'd have to do $30 million worth of business in Georgia. We may have over the last 12 years total, I doubt it. And I certainly know none of my competitors have, in order just to pay for the testing and break even on that one aspect of the business. It's just simply a financial reality that that can't be done. That's what makes, for example, NJDEP and ETV so important. NJCAT, the TARP, is accepted in 17 or 18 states. They lose some and gain some from time to time because they don't want to force a manufacturer to have to spend a ton of money. Hey, it's been tested. Yes, the rainfall's a little different. That can be worked out. The soils might be a little different. That can be worked out. So the financial realities come in. Until recently, there wasn't a published standard for scaling, meaning you tested one, how do you scale the rest? I will tell you this, early on, a gentleman, Dr. Gary Minton, and what we're, by the way, we're going to take the list of people that have been in this seminar today and all of those this year. And at the end of the year, we're going to randomly select 2. And if you've been in 10 seminars, you'll be on the list 10 times, so you've got 10 times a chance of doing this. I'm going to, Dr. Minton's book is around $150 or $175. It's the best textbook I've seen. It leans toward no product. It's simply the unit processes and operations of the chemistry and physicality of water quality. I use it a lot. I learn from it every day. But Dr. Minton convinced me in about 2004 or so that surface loading dominated the way particles came out of devices. And the long story made short, when I went to the city of Marietta, we came in with a published scaling. We said we're not going to load it at over 31 gallons a minute per square foot, something like that. And we agreed on that. And we said to the city, we will never violate those engineering principles. All of our devices will come in that way. Now, I know Marietta and others have standards, and they say, look, you have to tell me how you engineer inside your device. And I don't believe there's had been until recently a kind of a consensus out there, but it's starting to happen now. There's 2 really main methods of scaling a device. One's based on surface loading called HLR. This is what Dr. Minton convinced me dominated my devices. And just as an aside, I'll tell you how I disagreed with him quite strongly. And I can tell you today there's still plenty of SWEMA members that disagree with that quite strongly. But he told me to go to my own data, my field testing, my weights. And I found out that my devices that had the lowest HLR collected more pounds per acre per year than the ones that had a higher HLR. In fact, there was a sweet spot. We found out the sweet spot was around 24, 25 for my device, gallons per minute per square foot. And that's kind of what we've decided we designed to. In all jurisdictions, we're generally under 20 anyway, based on some other things. The high flow, because we're a stay online, can change that. But 6 HLRs is the way we went. And there's other people that based on scaling on volume, which is sometimes called exponential scaling. Suffer me just a minute of math here, please. Because people understand, they don't understand where these N factors in scaling come from. Because some people say, I use an exponential scaling factor of 2.5 or 3. Surface loading, HLR says if you double the area of a device, everything else being equal, you can double the flow capacity. It is a very simple equation. It's Q, the flow, in gallons per minute, divided by the length times width in square feet. So a 2-foot by 2-foot device has 4 square feet. And a 4x4 device has 16 square feet, so it should, by surface loading, be able to take 4 times the flow, all other things being equal. To get the area, you square the 2-foot dimension or square the 4-foot dimension. So the N scaling factor is 2. This, by the way, gets a little confusing for people when you go to round devices, but if you think about it, area equals pi r squared. R, the radius, is a size of the device. R squared in scaling factor is 2. So if you have a 2-foot circular device and a 4-foot circular device, you will find if you do all the math, it comes out exactly the same ratio. Volumetric scaling, you would take a 2-foot by 2-foot device with a depth of 2 feet. This is 8 cubic feet. So that same device at 4 by 4 by 4, 4 foot wide, 4 foot long, 4 foot deep, would be 64 cubic feet. So considering the volume, not the footprint, the volume, the device is 8 times bigger. Okay? So, excuse me, the device is not 8 times bigger, it's 16 times bigger. 2 times 2 times 2 is 8, 4 times 4 times 4 is 64, which is 16 times bigger. This is a scaling factor of 3. So people have said, you know, you have to look at the depth of my device. And the question is, can that actually be demonstrated in the laboratory in the field? It's very interesting because laboratory curves are not straight lines. HLR would tell you that your performance curve would be a straight line. Double the speed, half the performance. Half the speed, double the performance. Well, the center part of laboratory curves are straight lines. But in the beginning, depending on the size of the particles, the device catches everything. So the curve flattens out toward the top. And as you get lower, suddenly resuspension and other things start to wash stuff out of your device. And the curve flattens out on the bottom. So there are, the laboratory curves are very close to what HLR would predict, but they certainly don't follow volumetric or exponential curves. In other words, it's a kind of an S-curve, like the flow in a pipe, but it's certainly not a parabola or anything like that where there's a steep increase or a steep decrease of performance. So overall, HLR seems to predict loading results much better than exponential, and lab data kind of shows that. And there's some debate. I'll be not being honest and fair with you if I didn't say there's debate. The common sense reason for this, if you take the same device, a 4-foot round device is fine, and it's 8 feet deep, and then you make it 16 feet deep, a volumetric scaling guy will tell you that you've at least doubled the capacity because of the math. The fall rate of particles is constant, so making a device twice as deep means the particle has to fall twice as far. So the volume advantage in resident time, the water would obviously stand there twice as long, it's twice as big. It's canceled out by the greater fall distance. You can look at Dr. Minton's book or a million others. And in fact, if you're a wastewater treatment guy, you're probably going, yeah, it's surface loading. John's right. And to the extent that we're talking settling, yes, it is. You have to keep in mind always diffusion, washout, and velocities. That's where you lose materials. And in a BMP, we're talking net. So the major agencies have recognized this. And they've examined hundreds of laboratory and field test runs. This was not done by SWEMA. We could not come to a consensus here, really. But there is a consensus among the agencies that rate and talk about how to size devices. In December 2011, South Carolina, DOT decided to level the playing field and assure that water quality is being achieved, and the extremely competitive world bidding road jobs. Now this new protocol is being, people are applying for approval under it now, but they adopted an HLR-based specification. They say a device should be sized at no more than 20 gallons per minute per square foot. They're a little tougher than I am to be acceptable. They will accept it, I think, up to 26 or 28 if you can advocate for a particular reason. It's a super clean area, whatever, another BMP downstream. But no longer can a 4-foot round device with self-testing credentials replace a 12 by 6 foot rectangular vault that has third-party testing to verify it. Now, for everybody in our industry, whether they're land-based or manufactured or proprietary, this is good news, because we're going to suddenly be looking at apples to apples across the board. In September of 2011, New Jersey, NJDEP rescinded all approvals that were based on exponential or volumetric scaling and determined that all tested devices would have to use area scaling, or HLR, to size untested models that were larger or smaller than the tested device. To the credit of some manufacturers, in fact, I believe a majority, their approved flow numbers did not change at all because they had always relied on HLR for scaling, and this included ground devices and some of the ones you would know the name of. I will let you go look at the NJDEP testing, NJDEP testing, to see which devices changed and which devices didn't. But it will tell you a lot about the science and about the validity of specifications in the market when you look at individual companies and whether or not they were affected by this. To a black box magic salesman, enforcing a scaling standard is not good news. They've had to take down charts off their websites. They've had to revise literature. I went to some places just yesterday looking at their flow tables, and they're gone. They've got the size. They've got every other piece they used to have, but the flow's been whacked off of their website. And so it is difficult now with these, with the most used protocol out there, now saying you've got to have scaling. Now, understand this. There will be people with good devices. I can think of one that uses a lamella plate approach that can demonstrate scaling that is different than HLR. And I don't know if you guys are familiar with coalescing plates in oil separation, but it's a fact. You can take an 80-foot long gravity API separator in an industrial environment where you get mineral oil out of water and replace it with something much smaller by using parallel plates. There's some maintenance issues and some other stuff, but it's just a fact. There will be people who will provide laboratory evidence of scaling, and more power to them, but that's what's going to happen today. No longer can you just get out your calculator and start using an N factor of 3 and using cubing your performance so that something twice as big works 4 times as good instead of twice as good. No longer can you do that at most of the places. So NJDEP is probably the most used level playing field for lab testing. Understand, most of those guys up there are still only certified at 50%, but they have until September 11th of 2013 to bring their testing into line, to finish some field testing and to get verified. And that is a piece that, by the way, in looking at specifications, I see this all the time. In the state of New York, we will go in with an 80% verified solution. The engineer will put us on the plans. Someone will come in and go, look, my NJDEP testing shows I can run at faster than the crystalstream, the same size. Yes, but if the regulator took time to go look at the test, which they don't, and if they could understand all the mumbo jumbo of performance curves, et cetera, which they might not, even at the end of the day, if they came up with a number, yep, they can run 3 CFS, and they looked over at the certified removal rate of 50%, they would realize they're not doing apples for apples. I will tell you, you can run twice as fast as an 80% device and remove 50% based on the particle size distribution. So it's going to get more accurate, and that's the good news. NJDEP and others have realized that they need better protocols, and everybody needs to test the same. So today we're sitting there at 50%, regardless of how you test. The enforcement of scaling, and if you think about that, the enforcement of scaling has a much greater impact than how the test protocol was run. A small difference in particle size, whatever. Let me show you, and I picked out some products at NJDEP just to give you an idea. I've got the product, the size and model, what it was scaled at. I call that the Wild West, and what it is scaled at today. One product had its 4-foot model tested. Of course, scale to real didn't change because it was 1.1 CFS. Their 12-foot model, however, was published at 30.2 CFS, never tested, just simply using exponential scaling. Now that they've had to actually provide good scaling, it's at 10.1 CFS. And this is similar the whole way down. 5-foot model at 2.2 stayed the same, but when the scaling was addressed, the 27.5 became 12.6. It's similar to the first product, product C. And by the way, this came about because of competition. How could you go in with product C, 12-foot diameter, and say, well, it's really 9 because I'm using hydraulic loading rate. I'm trying to be responsible, and compete against the guy up top with 30.2. And the answer is you never would. And so these are not, I don't want to paint the picture that these are bad companies. These are folks that said, what's the standard? Well, the standard is use volumetric scaling and come up with an exponent that you like. That's changed, and that's good, because whether or not the 30 is correct or the 10.1 is correct, and that is subjective, somewhat subjective, if both products are on the same level playing field and then somebody determines what really works well for water quality, we're going to be way ahead of the game. So just keep in mind, one of the takeaways here is that here they test a small model, makes sense. It's much cheaper to test a 1.0 CFS, 450 gallon per minute in the lab. I tested, by the way, at up to 9 CFS, and it cost a lot of money for Alden Labs to build a test loop big enough to suit me, because they had been testing people at 1 CFS. And I told them I wanted to push my device to the 25-year flow, which was kind of interesting to them, and it was very interesting to me because I learned a lot. So just look at the HLR here. Now, I told you could run a lot faster than the 26 or so that I like today to get 50%. So the first model was tested at 39 HLR, and then its biggest device in that same product line was claimed to be able to run at 119.8 gallons per minute per square foot, and that's just crazy. It's now been reduced to 10.1, and the HLR is very similar to its test. In fact, their aim there was to make the HLRs exactly the same. The math changes a little bit. So once again, the HLR on the second product, 5-foot diameter, was 50.29. I could infer, since it's able to get 50% at a better HLR, that it might be a better product, because the first one could only get it at 39. Remember, I told you there's been differences in material, and so that 50.29 HLR only worked on some bigger material, but that's neither here nor there. Today, both of their models are approved for 50% removal at the same hydraulic loading rate. And again, the last one, HLR of 35.73, getting down into a range that could work well, almost for good water quality at 26. But if you take a look at these HLRs, you can see how far out of reality. Remember, South Carolina DOT says, after looking at all the testing and desiring to remove 80%, you better be at 20. So this will give you an idea, though, that what was in the past and what is today on TARP, for example, at NJDEP is much different. And that's something you need to think about. It will mean that you'll be able to, when someone quotes NJDEP or ETV or others, you're going to have better confidence in the fact that they've come in here with good testing. And just to break this up a little bit, I know I have to sometimes get a little geeky on the numbers, but when you hear something like we have an enhanced secret magic gravity settling using ancient fast fall hydrodynamics, and our device is bigger on the inside, the outside. I mean, this is the kind of thing, I've actually heard that first statement, that they enhance gravity by the way their device works, and that's pretty neat. If they could reverse that thing and run it backward to get anti-gravity, we could make a lot of money with it. And then the bonus feature, if you emulate the average storm post-peak FISBAR Coriolis effect, we avoid clogging your device with sediment. You get less maintenance cost because there's no sediment in your device. It makes it work a lot better. Now, I've seen 31-page reports of devices hydraulically loaded at 100 gallons a minute a square foot, showing that the entire benefit would be realized by using this device. And it's all mumbo jumbo, and there's not a piece of good science in it. So here's your takeaways. The test protocols are becoming standardized, and they're going to provide good comparative analysis. There's enough, the testing model is enough to provide sufficient data. You just can't do it physically from a cost standpoint. And of course, you'll never lab test some of them because they're field type public domain. And scaling is a critical issue. and it's now being addressed per surface loading in most jurisdictions. Last thing for me today is a word from our sponsor. We have always scaled by HLR. Our devices they average 18 gallons a minute per square foot with a maximum of 26 in general. We go to 31 in a lot of places as a top. We seldom get there. We want to keep that option open to us, but that's because we were tested by the ETV at 89% removal SSC analysis in Griffin, Georgia, and guess what? Now we're tested with TSS, that little test that I don't like so well, that little analysis I don't like so well. We were tested that way in Highlands, North Carolina at 96% removal. So when they made the test tougher, our device worked better. So it shouldn't be a surprise when you see the other numbers that devices are being put out that we have the best, by far, the best field testing on record of anybody, and that includes the canister media devices. So this is a banner we use at some of our shows, but we have a resume. You know, you may want to, if you're in the engineering business, may want to call your sales rep or call me and say, hey, send me your resume. And it shows what our qualifications and specifications are. So with that little advertisement out of the way here, I want to thank you guys for coming and tell you that we appreciate this very much. If you need PDF credits, Jeff will be on there in a minute. He'll tell you how to get that. And again, appreciate you being here today. And I'll be glad to take some questions. Jeff, I think if you get the president back, let me take this guy.
John, leave it up right now.
Okay.
Just, thank you. The floor at this time is open for any questions on the data that was presented. Obviously, there was a lot of different information in there and a little bit of our history. In the meantime, I will also tell everyone, please be sure to visit crystalstream.com and sign up for our newsletter. I know I've had a lot of people tell me, hey, I really want to know when the next webinar is or what's going on out there. I can't advocate enough. Go sign up for our newsletter. It's not going to be, you're not going to get spammed to death. It's going to go out once a month, but giving you what the class or what webinars are coming up, what's new in the industry, and what products are out there. In addition, if you're interested, under our download section, you can find our product resume, which reads just like a normal resume and can give you all the questions or comments and address any of your concerns. Appears not to be many questions, John. We have a lot of thank yous. One person did like your Dr. Oz.
Okay, good.
Said that was pretty funny. I said we've been working on your humor. But if there's no other questions, then thank you everybody for attending. You can email me at jbenty@crystalstream.com, and I'll be sure to get a certificate of attendance out to you. Thank you again, everybody, and have a great day. Our next session is scheduled for March 27th at 1 p.m. This is an old one we did way back when, stormwater management, what went wrong. So if you're interested, please pass the word. Thank you.